forward to be told the difference between no, we will all be told the difference between an impact model and a climate model, and we were going to be told this difference by Carla Behrendt. There you go.
Thank you. Yeah, hello and welcome, everyone. I would like to see my slides. Are these slides? Ah, okay, nice. So welcome everyone to my talk about climate modeling, the science behind climate reports. First of all, I will shortly introduce myself and what I do. I work at the UFZ, that's the Helmholtz Center for Environmental Research in Leipzig, and I work for the ESM project, which is short for Advanced Earth System Modeling Capacity. I'm also a PhD student at the University of Potsdam, and I'm part of the developer team for the mesoscale hydrologic model, which is an impact model. And I'm also a scientist for future and an artist. So what this talk is about, this talk is partitioned into 3 sections, mainly. First is the introduction, where I will introduce some nomenclature, like what is weather, what is climate, and what we can say about predictions, for example, why we can't tell the weather in 3 years, but we can say something about the climate, and what are climate models. Then the second part will be the longest, the science behind warming graphs. I will show you a graph that's typically shown when people tell you about climate change, and I will explain that graph in detail and what is behind it. The third part would be installing an impact model to your local PC if there's time. If there's no time, I will skip that. And in the end, there's, as always, a summary and conclusion. So starting with the introduction. Weather is defined as the physical state of the atmosphere at a given time, whilst climate is average weather. Most of the time, a time period of 30 years is taken for that averaging, but also other time periods could be taken. While the main question was, while we are not able to predict weather at a specific date in a decade, for example, let's say the 27th of December in 50 years or so, why does it still make sense to propose general trends for the climate? That is a question that often arises and I'll answer that. So first of all, it is about average. Average cloud coverage gives us information on average reflection, and average reflection is, has an impact on the warmth on the Earth. And the same is true for another scenario. For example, average precipitation, meaning rain or snow, and temperature has an impact on vegetation, and vegetation influences the carbon cycle, and that again influences the warming or cooling, and that has an influence on the ice coverage, and that again on the reflection. So there are lots of processes that are connected to each other, and if we know something about the average of some of this physical state of the atmosphere, we can say something about the climate trends. So the question is, what is a climate model? And the AR5 defines a climate model as a numerical representation of the climate system. The AR5 is a source I will cite quite often, so I have one slide with the whole citation. It's the 5th IPCC report. IPCC is the Intergovernmental Panel on Climate Change, and the 5th assessment report is, yeah, so AR5 is the abbreviation for 5th assessment report. But coming back to a climate model, so a climate model could, for example, be a GCM, a general circulation model, which is a global climate model that usually consists of ocean and atmosphere circulation. An RCM is not a GCM, but it's a regional climate model, meaning a climate model at a limited area, and mainly it has a higher resolution. And for it is at a limited area, that usually means that there is some input and output going in, because it's not a closed system. And an impact model, again, has usually a higher resolution in time and space, and it's not a climate model, but it's for simulating extreme weather events like floods. So if you want to build a dam or a dike, and you want to know how high this dike or dam should be, then you would usually run an impact model that gives you information about water heights over decades or longer or so, and then you would decide on the height. So this is the use for impact models. So that's for the introduction part. Now I come to the main part. And I will start with a question, is it proven? Or with a climate graph. As said, I will show you a graph, a typical image people would show you when they address climate change. This graph has an x-axis with a time scale, and you see it's reaching far into the future. And it also has 3 or 4 regions, and the first region is only in the past. And the y-axis is the global surface temperature change, meaning how much degrees in Celsius, or in Kelvin, if it's difference, it's the same, we will have in future, or we had already. And then you see several lines in different colors, and with the names RCP something. And I will explain all the numbers and everything about this graph, because it's a pretty important graph. So first of all, I will tell you, I will tell you something about the numbers and uncertainties. The uncertainties are the transparent colors behind the lines. I will tell you something about the representative concentration pathways, which is short RCP, and so it's reflecting the colors of the lines. I will tell you something about the source of the graphs, so where does these graphs actually come from? So I will tell you something about the assessment reports. And first of all, I will answer the question, is it proven or is there scientific evidence that we will face that climate change? So you will see that graph quite often. First of all, I took a definition for proof for scientific evidence from Wikipedia. The strength of scientific evidence is generally based on the results of statistical analysis and the strength of scientific controls, meaning you make an experiment over and over again, and you change basically some influences on the experiments where you want to know that this does not influence the output. So you can narrow it down and know what is the source of your results, and so you can prove a physical law or something. I took this comic from XKCD because it's a nice, it's somehow connected. So there's a person who pulls a trigger and then got struck by a bolt or something bad happens, for example, climate change. And then there are two scenarios. For example, a person usually would decide, okay, I would not pull the lever again. But scientists usually, or more often, would say, okay, maybe does that happen every time if I do so? Because, that's basically how you prove something, or that's experiments. But in case of climate change, even scientists say you shouldn't, although it's pretty interesting from a scientific perspective. But the problem is we only have one Earth. We cannot do this experiment very often, except we had a time machine. Then we could go back. But we haven't, so we shouldn't do that experiment. And that's something scientists before, long ago in 1957, said already. Human beings are now carrying out a large-scale geophysical experiment of a kind that could not have happened in the past, nor be reproduced in the future. So another question is yeah, if you ask this question, if it is proven or that it probably is not happening or so, to climate deniers, they usually would tell you, okay, maybe it's not happening, and the other side would take the position and ask you, okay, if you stand in front of a road and you want to cross the road, and there's a car approaching very fast, would you cross that road? Because it could happen that that car stops or makes a U-turn or something, but, well, usually it doesn't, and sadly, we know lots about this this experiment because it's done very often before we know something about traffic, and that is pretty dangerous. So let's change the factors a little so that we don't know so much about that situation. Let's say a cube approaches us with a high velocity on something that is maybe not a road. Would you still cross the something? And the answer is you still probably wouldn't. And why wouldn't you do so, although you know nothing about the situation? Well, you do know something. You know conservation of the momentum, which is a physical law you know about. So you have a situation you know not so much about, you have never had an experience before, but you still are able to make some assumptions because you know the physical laws behind it. And that's basically the same we do with, in the context of climate. So we have, let's say, just an Earth and the Sun, has some radiation, and that comes to the Earth and gets partially reflected, and the Earth radiates itself because it has some temperature. We know something about this Sun. We know the solar installation, and we know parts of the light is reflected, and the factor that is reflected is usually called albedo. So the reflected energy is albedo times the solar insolation, and albedo is something about 30%. And we know then that the light that is observed must be all the remaining energy. So the energy of the surface is 1 minus albedo times the solar insolation. Then knowing Stefan-Boltzmann law for energy emissions, where the temperature goes into the power of 4, and with the Stefan-Boltzmann constant, we can actually find out the surface temperature, which then is derived to minus 19.5 degrees Celsius. Well, probably we know, that the Earth is much warmer, and that's because our model in this case, which is maybe a climate model, is far too simple. So we change something about that. We add atmosphere, and atmosphere has some interesting impact. So atmosphere has some trace greenhouse gases, for example CO2, but also H2O, ozone, methane, O2, and nitrous oxide. And these greenhouse gases reflect the radiation of Earth back to Earth, partially. Meaning the atmosphere has a transparency, and this transparency, we call T, is something between 15% and 30%, so it's not fixed. And that's another interesting fact. The atmosphere emits energy, which we call J-atmos, and that goes out in space and to Earth. And the energy that goes into the atmosphere is 1 minus the transparency times the energy. So we know 2 equations. The first is the energy that goes into the atmosphere also goes out of the atmosphere. The second is that the surface temperature, the surface energy of the Earth is the term we had before, 1 minus albedo times the solar insolation, plus the one part of the energy that is reflected by the atmosphere. And so we have 2 formulas, 2 equations with 2 unknown, and with the Stefan-Boltzmann law from before, we can derive the surface temperature, which is 15 degrees of Celsius. And that actually is not so far from what it actually is. In 2000, it was measured that the surface temperature is 14.5 degrees. So I did this for a specific T, which is 22.5%. But when we change that T a little to, for example, 20%, so we add more CO2 because, for example, we would add a factory that would do carbon emissions, then the transparency goes down and the temperature rises to, for example, 16.6 degrees in case of 20%. This is also a very old knowledge. So this is maybe a little much on a slide, but it's still very interesting because it's copied directly from a paper that was published from Svante Arrhenius in 1896 already. And it's on the influence of carbon acid and the air upon the temperature of the ground. And carbon acid is the old term for carbon dioxide. So if we have a look to the percentage, so he investigated what if we change carbon dioxide? So what is the impact of our behavior? Let's say carbon dioxide would, the carbon dioxide in our atmosphere would double, so that would increase by a factor of 2. Then the average temperature rise in Leipzig in December, Leipzig, I choose the region for Leipzig, would be 6.1 degree. Well, that's probably a little high, but what we can see is already that Arrhenius back then already knew that there is seasonal impact on climate, climate change is seasonal and also spatial. So it is not just not the average temperature is the only interesting knowledge we get. So Arrhenius said something like, the temperature in case of carbon acid doubled would be around 4 to 6 degrees, and the current models predict something like an increase for 2 to 4 degrees for that scenario. So there's maybe an overlap already with that simple model from back then. So then I come to the question, a climate model represents physical laws, that's what we learned. Where do the uncertainties come from? So if we know all the physical laws and we would just calculate everything with these physical laws, why are there even uncertainties? And there are some reasons for that. For example, the initial conditions is one main source of uncertainties, meaning how is the current state of the climate system now? How fast does something move? Where are the clouds exactly, and so on? We don't know these precise initial conditions, and therefore from errors occur. Second would be the resolution of a model, so the temporal and spatial step length, meaning we can't we always represent our climate system with differential equations, and we approximate everything. We have not the movement of every molecule, but we have some average on cells. And if we increase the resolution, then usually the uncertainties go down, but sometimes they even don't. For some questions, it's better to have a lower resolution, but mostly it's better to have a higher. Then truncation. So we have computational limits and lack of understanding. For example, clouds. Clouds are not understood pretty well, and when I read the fifth assessment report, I found a sentence I found a little amusing. Clouds in climate models usually tend to rain too early. Yeah. So, but if you know all these sources of uncertainty, why is there no such thing as the one best climate model? Meaning, why can't we go to the highest resolution and to the best the best computer we get and do everything just in the best way, and then we would have our best climate model? And there are some reasons for that. For example, the so-called dynamic core, including the method for differential equations, or something like grids. For example, if we have triangular grid or rectangular grid. On rectangular grids, we usually can calculate faster, but on triangular grids, we could, for example, increase the resolution locally. That might be differences. And both has advantages and disadvantages. Also, the parameterization. Parameters, and our last slides were, for example, the T and the albedo, which will probably be not the final parameters because they are derived from other parameters, but physical laws or something are often represented by rules with parameters, and these parameters can be estimated. And they can be calibrated with different error measures. And this is another reason for uncertainties and differences in climate models. And then there are schemes. For example, there are different formulations of physical processes, for example, again, clouds. And last, the truncation again. We can also decide how we limit due to our lack of computational power. So, yeah, what do? We investigate all the models we have. So there are different climate models that are representing our climate. And we take all the models that match certain conditions, I come to that later, and we average the output, and then we get a climate projection and also that uncertainty band you see. So, what climate models do we investigate? They are so-called coordinated GCMs, or so climate models are compared in so-called coupled model intercomparison projects in different phases. These coupled model intercomparison projects are called CMIP 4, 5, and 6. So there might have been for early ones, but currently for the AR6, so for the 6th assessment report, CMIP 6 is investigated. And for I showed you on the map the research centers which took part in CMIP 6, so which take part in the 6th assessment report. These research centers are mainly specialized research centers, university and meteorological offices. But in general, it's open for any institution to participate as long as they follow a protocol for their contribution, where there's some rules, so you cannot just do anything. These institutions need to produce variables for a set of defined experiments and a historical simulation from 1850 to present. This blue part is a link, so if you go to my slides afterwards, you can see these variables you need to reproduce. And then you can do something like this. So we have a graph here again. On the x-axis, we see again a time scale that reaches from 1850 to today. And on the y-axis, we again see the temperature anomaly, or the temperature difference between, exactly the temperature difference, so how much the Earth has warmed up. We see CMIP 3 and CMIP 5 compared, which were the models that were investigated for the AR5. So we see a band, these uncertainty with the yellow and bluish in the background, and then we see these two lines, the blue and the red one from CMIP 3 and CMIP 5, and then we see the black one, and that is what actually was observed. And we see that this differs quite a lot, and that's due to there was only investigated the natural forcings, meaning excluded what the human did. And if we also put the human forcing into it, then it's quite matching. And that is the best kind of proof we can get. And again, I said, we investigate the physical laws, and the physical laws were actually results of scientific experiments, And so, yeah, there is this kind of proof. And, yeah. So maybe a little addition, there are also other coordinated model intercomparison projects so outside of the IPCC. One are inside the IPCC where the scientific focus is on subtopic, on something like land surface, for example, and that's what I do. There are also there's also published work outside from IPCC. So back to the graph. We talked about the part, is it proven? And I hope I convinced you that it is. And now I will talk about the sources of the graph. So I talked a lot about the IPCC. The IPCC, the Intergovernmental Panel on Climate Change, publishes reports. So the fifth, for example, the fifth assessment report, and what you see here is part of the cover. But there have been 4 ones before, as the name fifth suggests. The first assessment report, FAR, was published in 1990. The second, SAR, in 1995. Then there was the TAR, and then for the fourth assessment report, they changed the name scheme for some reason to AR4, and then there was AR5, which I'm talking about. The IPCC consists of several working groups, including working group 1, 2, 3, providing the assessment reports, and I mainly focus on the assessment report from working group 1, which investigates the scientific aspects of the climate system and climate change. But there's also a working group investigating on vulnerability and economic impact, and the third one on the options of limiting greenhouse gas emissions and others. So I shortly show you a history of the climate models. In something the mid-70s, climate models were investigated where there was just an atmosphere, the sun, rain, clouds were missing, and CO2 emissions. And I hope you believe that the sun is behind the atmosphere and not in this atmosphere. In the mid-80s, there was prescribed ice added and already clouds and land surface. And yeah, you see a nice mountain, but actually in that time, the resolution was so low that the Alps only had 1 or 2 grid cells, meaning there was not so much about land surface, but it was added. And for the first assessment report, there was a swamp ocean added, meaning an ocean was added, but it had no depth. For the second assessment report, the ocean got some depth, so it was a normal ocean with surface circulation, and there was added volcano activity and sulfates. For the third assessment report, there was added, so this is all about which kind of processes were there on climate models that were investigated in this assessment reports, meaning there were climate models before that already had those processes included, but they were not investigated in the assessment reports. So this is a history of which climate models or which processes in climate models were investigated in assessment reports. And the third assessment report, there was another circulation added for the ocean, the overturning circulations, and there were rivers added, which is interesting because I do something with rivers, and there were aerosols added and a carbon cycle, meaning that the carbon that goes into the atmosphere also goes out, but yeah, not everything, or the half time is not so good. For the AR4, there was chemistry added in the atmosphere and interactive vegetation. And for the AR5, there was ozone added and biomass burning emissions. And there's a history of processes, but there's also a history of computer modeling that might be really interesting. It started more or less in 1904 with Wilhelm Diakens, who found equations that could be solved to obtain future states of the atmosphere. And he thought about that, yeah, maybe these equations are really hard to solve, and that task should be split and distributed to many people. So he basically imagined a human computer. And then Louis Fry Richardson came in 1922 and did actually calculate all this, did a 6-hour forecast solving the equations by hand alone in 42 days user time, meaning he himself calculated 42 days on it, but that 42 days were distributed over 2 years in total. So he was a little behind the weather, only to find out that it didn't give the correct answer. That was long forgotten, but people said, yeah, that's not quite practical, we cannot do that. But then computers came in 1950. The first successful weather model was run on a computer called ENIAC, and in 1950, weather predictions were run twice a day on an IBM 701. Nowadays, we use supercomputers much larger, and yeah, there's a whole list and a rank, and I will shortly introduce JULES to you, the Jülich Wizard for European Leadership Science. That's a supercomputer in Jülich, and I would have shown you a picture, but you are not allowed. You are not simply allowed to take pictures on that campus. Since supercomputers are fancy, shiny cupboards anyway, I thought this is okay. So we have these cupboards that look like shiny cupboards, and in these cupboards there are blades, and each blade is called a standard node, and consists of, in case of JULES, 2 times 24 cores with 2.7 gigahertz. And it's hyper-threaded, meaning you can actually run 96 threads or processes on one of these nodes. And these nodes have 12 times 8 gigabyte of RAM, memory. And that's not quite much if you want to run a climate model, but I will come to that a little later. And in fact, in case of JULES, you have like 3 rows of 5 of these cupboards or something. And so there are in total 2,271 standard nodes, 240 large memory nodes, and 56 accelerated nodes having something like GPUs. And I tell you about JULES not because it's the fastest, actually it's maybe the 30th. Not even because it's the fastest in Germany. It was when it was built, but that's a while ago. But I told you about that because JULES provides actually a computing budget for the ESM project, the Advanced Earth System Modeling Capacity, and so there are actually Earth system models run on that machine. So what I told you before, there's not so much memory on each node, so what you need to do is you need to cut down your problem and distribute it over the nodes, and then there needs to be some communication. So usually you, if the task is so simple, you can cut down your grid and put a number of grid cells to each node, and then there is communication between the nodes on the boundaries to solve the differential equations. Talking about grids, I would talk about the resolution. Also, again, a history of resolution of the climate models. For the first assessment report, the resolution was 500 kilometers times 500 kilometers. And as I said before, you see these 2 yellowish cells in the middle that are the Alps. For the second assessment report, the resolution already doubled or halved. Depends on how you want to phrase it. For the TAR, it was 180 kilometers, and for AR4, it was 120 kilometers. For the AR5, it's a little bit a different section I show you. and also I show you two resolutions. There is the resolution for the higher models, which is 87, for example, 87.5 kilometers, and for the very high resolution with 30 kilometers. And that's because climate models are not just one model, but there are different kinds of models that are coupled, and each model has its own resolution. So it's more or less like something like this. So we have a model for ice, we have a model for atmosphere, for ocean, and for terrestrial. And this is coupled, so they all send their data to a coupler or something, and that's set to the, as an input to the other model. So this is more or less like how climate models look. And each of the models, again, has several layers. For example, the terrestrial layer has a groundwater part and the atmosphere. And so there's some input from the atmosphere to the soil and plant system, and then there's some water that is sinking into the groundwater and then coming out to the rivers. Yeah, so then we have the runoff, so meaning rivers get water, and then if you have a look to rivers and want to parallelize rivers, then it's not so easy because we have a source somewhere, and the water has to go from the source, or something that happens at the source has an impact to the sink, meaning this has to communicate all the way along to the sink. And that's where I come in. I actually do, so I show you the Danube, which you probably know better with the name Donau, at a resolution of 5 kilometers. And I basically cut down the Danube into sub-river domains. And we need, if we parallelize these, we need to calculate the sub-river domains that are farther away from the sink first. And you see that in the first graph a little. So the grayish areas are calculated first, and then it goes down farther to the sink. So just to tell you what I do. Now we come back to the main question. So we answered where the sources of where the graphs come from. Now we answer the questions: what is a representative concentration pathway? Meaning what we all did before was more or less telling how we get to that black line in the first section, and now we concentrate on the colored part where we have more graphs than one. The Working Group 1 of the IPCC generally tests a selection of coupled climate models, that is what I told you before, matching specific conditions, and investigates the output assuming different emission scenarios, meaning we have coupled climate models that are somehow different, for example, in their grid, and then we have input data. The input scenarios would be, for example, the first one, where we just do business as usual and don't reduce carbon emissions. The second would be we start with our way we do it today, but we would slowly change to renewable energy. And the third one would be a scenario where we do it spontaneously now or so. And that is an input scenario that we put into the systems, and then we get out a model output that says something about the future. So there's a black line that says, okay, this was our history until today, and from that on we have 3 scenarios, and they represented upper to lower. So the upper and right line represent the way where we do nothing or so, yeah, so this is basically what we do with scenarios. And the RCPs are scenarios. The RCP, representative concentration pathways, are scenarios that include time series of emissions and concentrations of the full suite of greenhouse gases and aerosols and chemical active gases, as well as land use and land cover. So that is another graph from the AR5. It shows again in the x-axis the years. It's the same time scale as before. But on the y-axis, we now have the radiative forcing that is basically having this impact on our climate. And so each of the RCP scenarios has some kind of equivalent in radiative forcing. And so we have four of these scenarios. The data for the RCP scenarios is coordinated by, again, the input form MIPS, input database for model intercomparison projects that I told you before. And most of it is freely available, and I gave you the link. So if you want to run your own climate model and test it with these input, you can find it there. And now I will explain the last part, the numbers and uncertainties. So first of all, again to the graph from before, the numbers behind the RCP refer to the radiative forcing at the end of the modeling period of 2100, meaning if you follow one of these lines, for example the red one, to where it crosses the 2100 line, then the number there is 8.5. So RCP 8.5 is the name for this RCP scenario. Then the numbers in these different sections are the numbers of models used for this scenario in this time period. As I said, there are lots of models compared, and we even have different models for the different time periods. So until 200 and 100, there are 39 models for the RCP 8.5, and for all the rest, there are 12. And you see this little gap, this line break at 200 and 100, 2100, and that is caused by the change of numbers of models that took place, that took part in this project. And another interesting thing that we see here, and maybe the most important, is we have quite huge model uncertainties. So if we compare all the models, there's a huge band where we can't exactly say, okay, it's like this or that, but this band is still, but human uncertainties are more important than these model uncertainties. We see tiny overlap, but mainly we can say how the human behavior derives our future, and that there will be this climate change we are talking about. So that was the main part about these three parts, and it is also the most important part. Now I could probably show you how you can install an impact model to your local PC, but probably I will I have maybe something like 3 minutes left, and we'll switch to the conclusion. Maybe if it's arising as a question, I can do it. So what have we learned? Weather is the physical state of the atmosphere at a given time, while climate is average weather. It is over 30 years. A climate model is a numerical representation of the climate system. And we learned that the main uncertainty is the way we solve differential equations. I would probably have told you what a differential equation is in particular, but that would have taken maybe another lecture. Climate change is not proven throughout repeating a real experiment over and over again. So there is only one Earth, as said. But models simulate our past climate pretty well based on physical laws that were proven in real experiments. And then maybe the most important message: human behavior is the primary source of climate change. Therefore, we talk about projections and not predictions, meaning if we wanted to predict the climate, then we needed to simulate all human minds and what we will decide in future, but we don't. That would be another talk again. We take what human will decide in future as an input scenario, and with these input scenarios, we create different output scenarios. So with different input scenarios, we create these different output scenarios where we can tell, okay, when we behave like that, this is the output. And human behavior scenarios dominate model uncertainties, meaning the question is, what do we want? And if you go to a demonstration, the answer is usually climate justice, and I think that is a good answer. Thank you.